Swayam Prabha. Digital India. Educated India.
The conclusions out of this. So first thing is that the width of the boundary layer width goes to 0 as epsilon goes to 0. We saw that in this solution here because the boundary layer was x by epsilon. So the width goes to 0 as epsilon goes to 0. And then, so another implication of this width observation is that the solution changes rapidly inside the boundary layer. Inside the boundary layer. The other observation that I have is that if we have boundary layer, the presence of boundary layer implies that we will have we need to take large number of grid points to solve the problem numerically. Large number of grid points to solve the problem numerically, and if we want to multiply epsilon when it is multiplied with the highest derivative term, we cannot just conclude that boundary layer is due to the multiplication of the highest derivative term with epsilon. That is certainly not true. Why? Because I'll show you one example. So epsilon when multiplied with highest derivative does not guarantee boundary layer, right? So one example at hand is the following equation: y double prime epsilon plus y is equal to 0, and we can see that epsilon is multiplying with the highest derivative term, but the solution to this problem is y is a linear combination of sine and cosine x over square root epsilon plus b times cos of x over square root epsilon. So this is certainly not a boundary layer solution, but only rapidly oscillating solution. So this is certainly not boundary layer, but rapidly oscillating solution. Okay. So this is what we have. So now, a problem involving boundary layer could be, we have to identify the location of the boundary layer in the problem. The boundary layer could be either on the left or could be on the right, or it could be on the both ends. But basically we will have to figure out where the boundary layer lies. So let us look at various problems involving these boundary layers and try to figure out the solution in each case. So the problem here is the boundary layer at the left end, we have that epsilon square y double prime plus y prime plus epsilon y square is 1 plus x. And again, if we were to, so x is between 0 and 1, and the boundary conditions in this problem are y of 0 is minus 1 and y of 1 is 2, right? So now we can again start to solve the problem. We eventually we can assume the solution of the form e to the power rx. Then we will get a quadratic equation for r. We can solve for r. We will eventually get, using the boundary condition, we can eventually get the solution in the form of r. We can plot the solution, and in this case we will see that the boundary layer is at the left end, or at x equal to 0 end. That is after plotting the solution. Now, if we don't know the solution, we could have either assumed that the boundary layer is on the right. So assuming that the boundary layer is on the right implies we are going to get an inconsistency. We will get an inconsistency, right? So again the step will involve that we are going to, the steps here will involve that we are going to assume an inner solution at x equal to 0, and we will assume an outer solution at x equal to 1, which is on the right hand. And for the inner solution we will use a singularly perturbed solution. We are going to use a rescaling of the variable x, and on the outer solution we will use a regular perturbation. We will use the regular expansion and we will find the answer. And then again, let me just not repeat the steps here, but let me write down the answers. For the inner solution, we see that up to the highest order term y naught comes out to be minus 1 minus b e to the power b 1 minus e to the power minus x bar, and the outer solution comes out to be y naught which is x plus x square by 2 plus a. A is also, from the boundary condition, a comes out to be half, that is for x equal to 1, right? And we see that here y naught is x plus half x square plus 1, right? So then what we have is, again we need to match the two solutions. The inner solution has to be matched moving towards the right. So this is y naught at 0 has to be matched at so what is happening? So again the inner solution has to be taken to positive infinity, because that is where the boundary layer is. So y naught at infinity has to be equal to y naught at 0. So this is where the y naught solution is applicable, and capital Y naught is applicable near the boundary layer. So when the capital Y naught is taken to infinity, small y naught is taken to 0, we get that b, the constant b, comes out to be minus 3 by 2. And then we are ready now. After finding the constant, we are ready now to write the composite solution to the problem. So the composite solution is y of x is y naught of x plus capital Y naught of x bar, capital Y naught of x minus y naught at 0, because we have to remove the overcounting of the constant. And after plugging in everything, we are going to get that the solution now is y of x comes out to be x plus comes out to be x plus half x square plus 1 minus 3 by 2 e to the power minus x bar, where x bar comes out to be x over gamma. So this is, x over epsilon. Okay, so this is my composite solution here, and that is applicable for the entire x from 0 to 1, right? And then what we have is that step number 2, I think that was in gist how to find the entire solution to the boundary layer problem, where the boundary layer is occurring on the left end of the problem. So now, how about we now try and look at a problem which involves boundary layer at both ends, right? So let us now look at a problem where we have boundary layer. So this is one example where we have boundary layer at both ends, and we see that this is epsilon square y double prime plus epsilon x y prime minus y is equal to 1 minus 2x, and we have that x is from 0 to 1 with y of 0 is 2 and y of 1 is minus 1, right? And then we have that the outer solution, again we are going to assume so this is a problem with boundary layer at both ends. Because suppose we don't assume that there is no boundary layer at any one of the ends, or we assume that there is no boundary layer at one of the ends, let us see what happens. So assuming that we have an outer solution, let's say y is y naught plus epsilon y1 plus epsilon square y2 and so on. We see that if we plug it into our original ODE, we see that the order 1 solution comes out to be y naught is equal to 2x minus 1. But this solution does not satisfy either the left hand condition or it does not satisfy either the right hand condition, right? So it does not satisfy any boundary conditions, and then what we have is that we have, so basically the conclusion out of this small exercise is we have boundary layer at both ends in this problem. Okay, so let us now assume boundary layer at both ends and see how to figure out the solution. So this was step 1 earlier. We checked that there is boundary layer everywhere on the left as well as on the right. And now to actually find the solution, we are going to have we will assume a boundary layer form of solution. So we will assume a boundary layer form of solution and we will match. So then the starting point is we will assume a boundary layer at x equal to 0, and we will now set our x bar to be x over epsilon to the power gamma, right? And which means that we have y at x bar. We will have to figure out y at x bar, right? So if we assume this rescaling of the independent variable, our new equation comes out to be epsilon 2 minus 2 gamma y double prime plus 2 epsilon x bar y prime minus y prime is equal to 1 minus 2 epsilon gamma of x bar. Right, so now we have how many terms? So let me call this as term number 1, term number 2, term number 3, term number 4 and term number 5. Of course, we can assume that gamma is greater than 0 here. Why? Because that's the rescaling we are assuming, and because we have a boundary layer at x equal to 0, so we have to scale out the factor of epsilon. So gamma is greater than 0 seems to be a correct assumption, and we have to retain term number 1. So we have to retain term 1. Why? Because that's the highest order derivative term, And notice that since gamma is greater than 0, and term number 4 is of epsilon to the power 0, and term number 3 is also of order epsilon to the power 0, we expect that term number 2 and 5, so both term number 2 and both term number 5 are of order much less than term number 4 or 3, right? So both term number 2 and 5 is of order much lower than term number 3 and 4, because gamma is greater than 0, right? So now, so that is true because gamma is greater than 0. So we need to match term number 1, because we need to retain it either with term number 4 or term number 3. We have only two options. So to do that, if we match term number 1 with, let's say with 3, we see that we will get 2 minus 2 gamma is equal to 0, or gamma is equal to 1, right? And now term number 2 and 5 is already of order less than term number 3, and term number 4 is of order term number 4 is also of order term number 3. So we have so this is going to work, right? So 1 matching with 3 is going to work. So we have found that gamma is 1, and we now have this rescaling that x bar is x over epsilon to the power 1, because gamma is 1. And if we plug it into our expression here, into our equation, we see that y double prime plus epsilon x bar, y prime minus y prime is 1 minus 2 epsilon x bar, right? So this is what we have. So after plugging all that the rescaled value of the variable, we are going to get that this is the equation. And now we can try and solve order 1. We will see that this is y double prime minus y prime is equal to 1, and from here we have the initial condition y0 of 0 is 2. So that is my initial condition, y at 0 is 2. So from here we can solve that y0 is minus 1 plus a times e to the power x bar plus 3 minus a times e to the power minus x bar. And we have that y0 is 0. So what we have is, so that is what we have. Okay, so then similarly on the so what have we got here? We have got one solution at one end of the problem. This is at x equal to 0 is what we have found. Now if we were to match, now we could match this solution. See, the problem is that we have boundary layer at the left end at x equal to 0 and boundary layer at the right end at x equal to 1, and in between we could have a solution which is regularly perturbed, and the regularly perturbed solution is already we have found to be 2x minus 1. So now if all we need to find is this constant a, and what we do is we do a matching of y0 at infinity, and we match it to the regularly perturbed solution y0 at 0. So y0 at infinity, and this is the solution y0, this is to be matched at 0. This is at infinity and this is at 0, and we see that y0 at infinity is minus 1 plus a times infinity plus 3 minus a times times 0, and this has to be equal to y0 at 0, which is minus 1, and we see that if we take a equal to 0, we are done. We are able to match nicely, and that is the value of a that we will take, a equal to 0. Okay, so my solution at the left hand is minus 1 plus 3 times e to the power minus x bar. Okay, and then so this is the solution at the left hand. The solution at the center is was of course 2x minus 1, that is through regular perturbation. How about at the right end? At the right end, we now have that is at the end x equal to 1, we now have to use a rescaled variable which is x minus 1 by epsilon to the power gamma, right? So x minus 1 by epsilon to the power gamma. Why? Because the solution has to be rescaled with 1 subtracted, 1 is on the right hand, and of course rescaled with epsilon to the power gamma. So what we see is, if we plug it into our equation, we plug it use in 3. So our equation number is, let's say this is our equation number star here, right? Is this what we have? No, so this is the equation. This is our equation number star here. So if we use this this scaled form of the variable in equation star, we are going to get an equation of the rescaled equation of the following form: epsilon 2 minus 2 gamma y. This time I am going to use y tilde, because y tilde of x is y at x bar, right? So this is this x bar I am talking about. Okay, so then this is epsilon 1 minus gamma times 1 plus epsilon to the power gamma x tilde times y tilde prime minus y tilde. This is equal to minus 1 minus 2 epsilon to the power gamma x tilde. And so now we have the terms 1, we have the terms 2, and of course term number 3 and term number 4 and term number 5. So we have lot of terms, and we will see that of course we need to retain term number 1, and we see that term number we have to keep gamma term number 1. We have that this particular term, term number 5 is the smallest. Why? Because gamma is greater than 0. So we can compare term number 1 with either term number 2, 3 or 4. And if we do that exercise, we continue doing that exercise, we will land up with the fact that gamma comes out to be 1, right? Gamma comes out to be 1, and plugging it into this this new ODE, we are going to solve. We will solve this ODE. We will see that this is y tilde double prime plus 1 plus epsilon x tilde y tilde prime minus y tilde is equal to minus 1 minus 2 epsilon x tilde. And y naught of 0 is minus 1, and we see that y naught of 0. So this is the left hand condition for the boundary layer, the inner solution, and from here again we can solve for the highest order term. So order 1 term, we will have y naught tilde double prime plus y naught prime minus y naught tilde is equal to minus 1, with y naught of 0 is minus 1, and we see that y naught tilde is 1 plus a times e to the power r plus x tilde minus 2 plus a times e to the power r minus x tilde, and we see that where my Rx, R plus minus, comes out to be the golden ratio. We solve where? We can easily solve this problem by plugging in y naught to be e to the power Rx and solve for Rx using the quadratic equation. We will get R having two roots, and then we can see that R of the first root at x tilde going to minus infinity will go to 0, and the second root at r minus at x tilde going to minus infinity will go to infinity. And so what we have is that for this value we need to have that a plus 2 has to be equal to 0. A plus 2 has to be equal to 0, and so that is what we have, right? And then what we have is that y naught comes out to be 1 minus 2 e to the power r plus x tilde. So this is my final form of the inner solution at so a comes out to be minus 2, and so that how we got that, so that we avoided any infinite terms. So a plus 2 has to be set equal to 0 so that any infinite terms are avoided. So with that, our inner solution is found out to be 1 minus 2 this factor, and now finally our composite solution comes out to be y is equal to y naught, that is the in between solution which is regularly perturbed, plus y naught at x bar, that is the left hand solution, plus y naught tilde at x bar, that is the right hand solution, minus the left hand constant which is over counted, minus the right hand constant which is also over counted. So then after plugging in all these values, we will get that this is minus 1 plus 2x plus 3 e to the power minus x over epsilon minus 2 e to the power r plus x minus 1 by epsilon, right? So we get this form of the solution that we have. Okay. So I think I'm all out of time in this session, and in the next module we will be looking at a particular form of we will be looking at a particular application of this regular and singular perturbation techniques, namely an application in the so-called area of continuum mechanics. So thank you so far for listening.